In this video session, we are going to talk about signal modulation. Okay, now modulation or signal modulation is actually a very important part of signal transmission, you can say, or signal communication. So whenever we are talking about any long distance transmission of the signal from one place to another, especially when we talk of telemedicines, etc., where sitting at a remote location, the doctors can actually look at the patient, the data is transferring, or so on and so forth. Even in a networked medical systems in within the hospitals, etc., wherever your data is actually traveling from one place to another, at that point of time, the signal modulation actually becomes very important. Okay, so modulation actually means the process of varying one or more properties of the waveform called the carrier signal with a modulating signal that typically contains information to be transmitted. Okay, so modulation can actually be defined as a process by which some characteristics of the signal known as carrier is varied according to the instantaneous value of another signal known as modulating signal. Okay, the signals containing the intelligence or the information to be transmitted are called modulating signals. These modulating signals contain information and are also called baseband signals. Also, the carrier frequency is greater than the modulating frequencies, and the signal which results from the process of modulation is called modulated signal. Okay, now over here, whatever modulation we are going to talk about, we can actually classify it into either amplitude modulation or angle modulation, and the angle modulation can actually further be divided into phase modulation or frequency modulation. So first of all, we are going to talk about amplitude modulation. So amplitude modulation is defined as a system in which the maximum amplitude of the carrier wave is made proportional to the instantaneous value of the modulating or the baseband signal. So the carrier wave, suppose we consider a sinusoidal carrier wave, that is A cos omega ct. A is the maximum amplitude of the carrier wave and omega c is the carrier frequency. Okay, so over here, we are having suppose xt denotes the modulating or the baseband signal. Then, according to the amplitude modulation, the maximum amplitude A of the carrier will have to be made proportional to the instantaneous amplitude of modulating signal xt. Okay, so the standard equation for the amplitude modulated wave is expressed as A plus xt cos omega ct. So over here you can see that the amplitude of the new wave is actually varying in accordance to the modulating signal. Your information carrying signal is xt. A is the amplitude of your carrier signal, and the final modulated wave that you are getting at the receiving end will actually have the amplitude of A plus xt. So at the receiving end, you know that whatever value you are obtaining for the amplitude, simply subtract A and you will get the value of the information signal. Okay. So this is what amplitude modulation works like. The modulating or the baseband signal xt contains the information or the intelligence that is to be transmitted. In the process of amplitude modulation, this information is superimposed upon the carrier signal in the form of amplitude variations of the carrier signal. This means that the information to be transmitted is now contained in the amplitude variations of the carrier signal, or you can say that in amplitude modulation the information is transmitted in the form of amplitude variations of the carrier. So whenever we are talking of amplitude modulation or any modulation, there is an important quantity or important value that is always to be kept in mind, that is modulation index. So in any system, the modulation index is actually defined as the extent of amplitude variation about an unmodulated carrier, and it is represented as MA is equal to maximum of XT, the maximum value that is present in magnitude in the xt signal, divided by the maximum carrier amplitude. So in the previous slide we had seen that the maximum carrier amplitude is A. So the maximum value present in your information signal in magnitudes, you can see there is a modulus symbol over there. So with the disregard to the symbol, whether it is positive or negative value, The magnitude value, that is the maximum in your information signal, divided by the maximum amplitude of the carrier wave, is actually called your modulation index. So you can say the numerator actually represents the maximum amplitude of your modulating signal, and A represents the maximum amplitude of your carrier signal. So the modulation index is also known as the depth of modulation, degree of modulation, or modulation factor. Okay, so next type of modulation that we can perform is phase modulation. Phase modulation is a type of angle modulation in which the phase angle is varied linearly with the baseband or the modulating signal about an unmodulated phase angle. So this means that in phase modulation, the instantaneous value of the phase angle is equal to the phase angle of the unmodulated carrier plus a time varying component which is proportional to the modulating signal. Okay, so now if you see mathematically, you have a carrier signal, that is A cos omega ct plus theta naught, or you can say A cos phi, where phi, that is the complete phase that we are talking about, that is omega ct plus theta naught. Okay, so if for simplicity over here we are neglecting theta naught, that means your phase over here is omega ct. Okay, now what we are saying is that we need to add into this existing phase phi a quantity that is proportional to the information that is carrying in your modulating wave, and your modulating wave we know is xt. Okay, so and if we have to make it proportional, so one proportionality constant kp multiplied by xt is actually added into your original phase phi, right? So if you see on your screen, you can see equation number 4.10. The new phi that is now you are getting is omega ct plus kp into xt. Xt is your information carrying signal. Xt is a signal which is actually carrying your useful data. Okay, so that value multiplied by a proportionality constant, and it is added into your phase of the carrier signal, and then it is transmitted. Okay, so this kp, that is a proportionality constant, is also called as the phase sensitivity of the modulator. So finally, at the receiving end, the equation that you are receiving is A cos omega ct plus kp into xt. So again, at the when you know this formula at the receiving end also, you can decode it in the same manner, because the phase sensitivity modulator of the modulator which will be at the transmitting end, the same we use at the receiving end also. So when you know all the other parameters, okay, you know the value of A, you know omega c, you know kp, so you can actually put all the values over here. S, of course, you know whatever value you are receiving in this, if you substitute all these values, you can find out the value of xt. Okay, the idea behind doing all this is that your original xt is actually a very low energy signal which cannot travel a very larger distance. So we are superimposing it on some high energy signal so that it can actually travel some distance, and at the receiving end we can decode it in some or the other way back into the original value xt. So in amplitude modulation, what we were doing is we were adding that value xt into A, and at the receiving end what we do, when you receive the signal, the amplitude of that signal, from that you subtract A, you get xt back. In this case, in phase modulation, what you do, the total phi of your signal, A cos phi, if I'm saying, that is your carrier wave. So in that phi, we are adding a quantity that is proportional to my information value. Okay, that is kp into xt. So kp becomes a phase sensitivity of the modulator, or it is a proportionality constant. So the final st, that is final wave that I receive at the receiving end, will be A cos omega ct plus kp into xt. So all the values, when I know, I substitute all the other values into this equation, I can decode to find out the value of xt. Right. Then we have frequency modulation. Frequency modulation is a type of angle modulation in which the instantaneous frequency is varied linearly with the message or the baseband signal xt about the unmodulated carrier frequency. That means the instantaneous value of the angular frequency now will be equal to the carrier frequency plus a time varying component proportional to the baseband signal. So earlier in the complete phase we were actually adding. Now only in the frequency component, that is phase, the complete phase, if you see, is actually omega ct plus theta. If you see equation 4.14, this complete bracket thing is actually the phase, right? And this phase actually has one component, time varying component, and that is frequency, right? So now in this particular type of modulation, what we have to do is this omega I, that is instantaneous frequency of your signal, has to have one component added proportional to your baseband signal. So now your omega C, that is your carrier frequency, plus kf multiplied by xt. In the previous one we had kp multiplied by xt added into your phi, that is a total phase. Okay, now here what it is, omega C, that is your carrier frequency, and it has got an added component that is proportional to your baseband signal xt. So this kf actually over here is a frequency sensitivity of the modulator, right? Now, so if you see over here, your original carrier signal that you have, that is a cos omega ct plus theta naught. Okay, so just to simplify, what we are writing is phase as phi. We are denoting the phase as phi, and this theta naught for the timing, just for simplicity we are neglecting. Okay, so at the end, suppose the frequency of the modulated wave that you are obtaining is a cos phi I, that is instantaneous phase angle. So now, no, we know that instantaneous phase is actually integration of the instantaneous angular frequency, that is phi I is actually omega I integration over time. Now what is this omega I? In the previous slide we have seen that omega I is actually omega C, that is the original carrier frequency, plus kf into xt. So in this particular equation 4.19, I substitute the value of omega I, that is omega C plus kf into xt, and integrate this whole thing with respect to time. What I get is omega c into t plus kf. This is a constant, this comes outside, and since x is already a function of time, this has to be integrated with respect to time. So the final wave that I get at the receiving end will be st, that is a cos omega ct plus kf into integral of xt dt. Right, so this will be my final wave. So in general, this is called as FM wave expression, that is frequency modulated wave expression. Okay, so we have seen that in general, you can just sum up that when you're using a sinusoidal carrier wave, any sinusoidal carrier wave has three parameters: amplitude, phase, and frequency. So according to my baseband signal, or you can say the information signal, I can vary any of these three properties and create a new signal, that is a modulated signal. When I change the amplitude, it becomes amplitude modulation. I add my information signal directly into the amplitude of the carrier wave, it becomes amplitude modulation. When I add my information signal into the phase, it becomes phase modulation. Okay, when I add a proportional value into the instantaneous frequency, it becomes frequency modulation. Okay, so these are the three ways of manipulating or modulating a carrier wave, with the help of which your information signal can be transferred to a larger distance, or it can be transmitted to a particular distance, and at the other end it can be decoded again. Okay, then we have an important quantity called frequency deviation. We know that instantaneous frequency of the FM wave is given by omega ct plus kf into xt. The instantaneous frequency varies with time around the carrier frequency omega c. So the maximum change in the instantaneous frequency from the average frequency omega c is called frequency deviation. Okay, so delta omega, that is the maximum deviation, is actually nothing but kf into xt, the maximum value of kf into xt. So from your omega c, you are having value. When you are adding to some proportional value, it might go up, it might go down. Okay, so the maximum limit up to which the values are changing is actually deviation in any one particular direction. So the maximum change in the instantaneous frequency omega I from the average or the carrier frequency omega c depends upon the magnitude and sign of kf into xt. This means that the frequency deviation would be either positive or negative depending upon the sign of kf, that is frequency sensitivity of the modulator. The amount of frequency deviation in both the cases is given by the maximum magnitude kf into xt max. Okay, you can see that there's a modulated, there's a mod signal over there. That means the magnitude only is to be considered, not the uh, uh, says not the sign along with that. Okay, or in very the maximum change, since we have to find out, the very simplest thing is that omega I minus omega c will actually give you the delta omega. That is how much change in omega I has taken place with respect to omega c. That is called the frequency deviation. So we'll be dealing with a lot of numerical problems related to these formulas in the tutorial class.